We are going to talk today about scientific visualization in VR. It's part of our, oops, I pressed the right arrow here. Oh, wrong focus. Oh. It's part of our virtual reality workshop series. And what is that green line? Does that mean it's not sending the whole thing? Sorry, I want to make sure that the whole thing is recorded. Let's see. Oops. Do you see the bottom of Alan?
Yeah, I see the photo.
All right, so that green line is meaningless. All right. Okay, so anyway, yeah, so part of our workshop series. And today we're going to do scientific visualization with VR. Next week, we're going to do specific to molecular visualization. We're going to have a guest speaker from the University of Illinois, John Stone, to speak about that. And so we'll talk in detail about molecular visualization then and have some examples. And then it'll be spring break. Then we'll have a week of a couple of demonstrations. And actually, we'll probably have to reschedule the March 25th one now that I look at it. But anyway, we'll do virtual tourism right after spring break. We're going to have another hands-on expedition, which will cover a lot of the same things we look at today, although more focused on education. And then we'll have another guest speaker from the University of Illinois, or a set of speakers to talk about archaeology training and application they developed. And then we'll close out with some Unity in VR. And then we have our sort of corresponding workshop that the Digital Humanities and Creative Arts group are putting on. And tomorrow is also going to be a virtual reality focus for them. And that will be presented by Matthew Brennan. And he's going to look at doing virtual reality and art history with some tools, some applications he's developed and are developing. And then the week after that, Margaret will present for VR and art. All right, but today is scientific visualization in VR. And so for those of you who weren't here the first time, so I'll do a little quick refresher of the medium of virtual reality. Mainly that, oops. I think this slide is slightly out of order, but anyway, so we're going to talk about immersive visualization, which is the bringing together of virtual reality and scientific visualization. And so we're going to talk a little bit, I'll do a little quick refresher of virtual reality and scientific visualization, but the first talk in this series, the medium of virtual reality, covers all the bases on that. But anyway, for a quick refresher, in that talk, we talked about 5 key elements of virtual reality, that the things that make up a good virtual reality experience. And so those are the participants, the people doing the experiencing it firsthand, the people who made the experience, the world, the contents of the experience, the fact that you have physical immersion, which means when you move your head around, you see something from a different perspective, you hear things from a different perspective, and the fact that you can do interactions with the world. And so here's the definition that we presented in that lecture. And it's kind of a long sentence here, but it's really broken down into these 4 elements, that VR is a medium. In particular, it's an interactive medium. It's based on tracking the user so that when the user moves their head, they get a different perspective on the world. We display back to the user, and therefore we provide this physical immersion. And last refresher topic is that there are kind of 3 classical styles of virtual reality and or augmented reality. The one that everybody thinks about today and that we focus on a lot because it's more consumer based is the head-mounted display style, where the displays are attached to the head. But on bigger systems, which we have some of these on our campuses, and a lot of companies will have this kind of virtual reality where you actually walk into the virtual reality display and the world is presented around you. It still falls into the definition of VR because the head tracking changes how the graphics are rendered. And then finally, we have displays that the user can hold, such as this augmented reality phone style application. So that's our VR refresher. Now we'll do a little visualization refresher, which goes back to last semester. The first thing I like to talk about with visualization is this notion of getting, whether you can see information by looking at the numbers or the fact that visualization graphically representing these numbers helps. This is 4 pairs of XY numbers that we'll see the plot for in a moment. For the most part, though, they kind of look somewhat random, except for this one column. X has obviously a consistent value with one outlier. But the thing to notice is that for all 4 pairings, there's 11 numbers in it. They all have the same mean for X. They all have the same mean for Y. They all have the same variance in X and Y. They all have the same correlation. And therefore, they all plot to the same line. And so if we look at that line as compared to the actual plot of those numbers, we see that there's quite a variance in what those numbers actually are, right? So the first one is kind of noisy, but it kind of follows our regression line. The second one clearly is not a line at all. It's more of a parabola, an incomplete parabola, but it creates this same regression line. The third one is a line that's, it is a line, but it has a slightly different slope than what we plotted because of this one outlier, but otherwise it's a pretty consistently different line. And then of course the fourth one, where we saw all the values for X as 8, is quite a different slope than the line we came up with because of one drastic outlier. And so there's the reason we want to see things instead of just look at the numbers. Now, a lot of times we'll want to go back and then reevaluate these numbers, but at first it's kind of good to get an insight ahead of time by graphically representing that. And so here's this visualization process represented by these 5 sub-pictures that represent these 5 stages, which is, first we have the phenomenon. This is in science visualization. Then we have the mathematical representation of that phenomenon with several partial differential equations. We take that and we create some computer code, hopefully not in Fortran, as we shown here. And then we run that in our computer, our supercomputer, and we get a bunch of numbers out. And then we take those numbers and go back to a visual representation, or a visual representation that hopefully, I should have had a slide here. I'm just going to go back. Hopefully more or less matches what the natural phenomenon looks like. And we can use that matching as kind of a test to make sure our formula and our procedures are valid. Of course, we don't have to represent it physically. We can then go in and take slices of data and look where fast-moving air is versus just the visible air from cloud vapor or from water vapor. And then we're going to add one more stage to that today then, and that's to add physical interactivity, specifically virtual reality physical interactivity. And so then we can see our weather patterns and stuff by moving around in it. All right, so those are our 2 refreshers, visualization and virtual reality. Now we want to motivate the bringing of those 2 things together, right? We have our physical immersion. We'll talk in a moment about some of the demonstrated values that it has as an interface for looking around, exploring spaces. And then visualization, which we want to take our numbers and represent them. And so we're going to take those 2 things and put them together, and hopefully we'll have something even better. Right, so we want to create some tools that make that easier to bring things together that are more consumable, right? All right, so, well, I know. Do you know the reference? Have you seen that commercial or YouTube versions of that commercial? Yeah. Which is where I got the picture. So why do immersive visualization, right? So it's a natural interactive exploration of the world, which we already looked at. And it lets you actually go inside your data and see it from within and see relationships. And I'll talk a little bit about some anecdotes of that in a moment. So what is the value then of immersive visualization? If you're going to spend some money, spend some time doing this, you want to have a hope that there's going to be something that benefits you in the end. And one of the things that isn't necessarily obvious, it wasn't obvious to a lot of us who were put visualization, virtual reality together, 20 years ago, and that's that for the most part, virtual reality isn't where you're going to go do your analysis. For a lot of scientists, they have their numbers, they want to do their statistical analysis on that, and they still need to do that if they're going to publish something and say that there is a correlation or a causation between things. And so really, you still have to do that. And VR is not where you go to run your statistics. Mostly it's like going and exploring, right? So it's going out into the field. There are still scientists who go out on field trips if they are studying weather or terrain or animals, flora and fauna. So they actually have to go out there. And so they go out there and they see, kind of make some observations of what's going on. Then maybe they put trackers on things and they have, or cameras to measure the height, the growth of plants or the movement of animals, things like that. And so we're out in that world to make important measurements, get some insights, and then bring that data back to our office, our computer, and then do the analysis there. And so that's really, I think, the key thing for where virtual reality has a value for scientific visualization. It does have other values. One is you can go and actually recon for an actual field trip, so that when you get out in the field, you know where you want to set up your instruments, or you have at least an idea of where the more likely places for success are because you've previewed them. And also, if you're taking out new grad students or something, you can get them up to speed on where you set up equipment in camp. So getting back to our role of immersion in visualization, we treat the VR system then more like a scientific instrument, I think, in most cases. So it's like you can have a microscope where inside the microscope, modern microscope, you can actually have grid lines or whatever and take measurements of cells on a slide, right? Or it certainly provides an alternate view. It provides I can't think of a simple English word, magnified view of the data, right? And so here in virtual reality, we get not just a magnified view, which we can do, or a scaled down view to see context. We can actually walk around and see it from different angles and see how two objects are related to each other. In some cases, we might take our data into VR and clean it or enhance it. We'll talk about an example of that later in the talk here, where sometimes we have like filaments, and computers are getting to the point where they can figure out paths for us, but in some cases there's a lot of overlap, and so it takes maybe some human intuition still for that. We may see that go away. Then virtual field work, right? So you can tour a reconstruction of a data set. So you've gone out, you've plotted the data. Maybe you have the data now of animals moving around a terrain, and you want to kind of watch that over time. And then, of course, the recon notion that we talked about already. So a slide that has changed quite a bit over the years of talking about this topic is the cost of visualization, of immersive visualization, right? So we generally talk about these days the notion of flagship facilities, which are big displays, tile display walls, cave-style systems, Cave 2 style systems, and commercial off-the-shelf systems, virtual reality systems, which are more akin to what people are going to be using today in their office, at their home, something that they can have even bring with them. Excuse me. So obviously there's going to be a lot more action happening in the consumer world, but there are still times and places for big displays, just like we have a room here with a big display on the wall, and it allows for sharing and conversation. So there are still good uses for flagship facilities. And then there's several different kind of levels of consumer. We have the higher end stuff for now, the Vive and the Rift. We have somewhat lower things that are more phone-based, like the Daydream and the Quest, which comes out, and then some augmented reality, higher end augmented reality systems, such as the HoloLens and Magic Leap. But for a lot of things, except for maybe the super expensive, well, actually even including these big display walls, a lot of the cost is really the time and effort that goes into developing the code, moving the data around, converting the data into a format that works well for visualization at all, and then it's particularly for immersive visualization, because we have a rendering requirement, right? So one of the big differences between virtual reality visualization and desktop visualization is that on the desktop, we can tolerate slower rendering, right? So if we have gigabytes of data that we want to see everything at once, if it goes like 10 frames a second, 15 frames a second, it's not super pleasant, but it's livable. But if you do that in a head-mounted display, that's kind of nausea-inducing. And so most consumer head-mounted display companies recommend 90 hertz as the rendering rate, which means less data. We can't see all of our data unless we have kind of a smaller data set. This requirement of 90 hertz actually isn't quite as high if you have a cave or an IQ wall, kind of flagship style system. And that's because the displays aren't moving. When the displays move, then we have to render a little faster. So one of the things we have to do for that is to somehow overcome the data limits. And so one way to do that is subsampling. And so this picture here represents level of detail on the fly sampling. So this is a point cloud database. You can see there's some regions where there's extra points in because from the user's point of view, so in this case, the user's kind of standing in the middle, they're looking at this region here, and so a lot more details have been filled in that region, and then the rest of it's kind of lower resolution. So that's one way to make things render a little faster until we get even faster computers. So in the case, especially in the case of flagships facilities, but even in rooms like this where we have 10 Vives available to people, you still won't need to ask the question of whether that value comes through as compared to the cost, right? What's your return on investment? And so a big question then is how much, the typical, say, bean counter question is how much is the facility going to be used? How much time per dollar spent is available? But after kind of working with immersive visualization for a long time, I think that a better question is, will my facility enhance the work that's being done? Even if that means someone goes in, I'll talk about an anecdote in a minute, where they go in, maybe use it for a few minutes, get an insight, their work in the VR facility is done, they go back and they actually make some great scientific accomplishments based on that few minutes in the VR facility. And so to answer this question, no, these are not the same questions, right? Because the amount of time being used isn't necessarily a measurement of effectiveness. And then of course, there are different ways that a VR facility can be used, and the ways that some of these ways do work better or are a better measure of how, or take a better measurement from how often they're used. And so in particular, training and education, the training of a mission or something like that, if someone's going in or educating on a particular mathematical equation, they want to be doing it first person. That's the whole point of the VR. In that case, they're trying to get kind of personal familiarity with some action or some system, mathematical system. And so in that case, you want them in the VR facility. They're not there just to get a one-time insight. Data analysis, again, you want to go in there maybe for the insight, but long-term, you're going to take that information back to your desk and do the data analysis there. Trip planning and recon, if you're going out into the field, you want to get kind of an overview of the land. And so in that case, you probably are going to expend, hours worth of time to get a kind of a good lay of the land. And then things like product analysis. So car companies use this kind of thing to look at a car. Then you're going to kind of want to walk around the car for a while, have a conversation with different members of the development team and design team. And so in that case, you're probably going to use the facility a little more. So another sort of example where the time involved in the facility matches that. All right, and so some of there's some papers which you can look up if you're interested that both experimentally and anecdotally kind of demonstrate that there is some value from immersive visualization. And so Fred Brooks's team at the University of North Carolina kind of started things off, and they did a paper where they had chemists do a study of how well a drug would dock with a protein. And they found, and this included with some haptic interface, they found that they were about, they give a measurement of twice as much, and that's, I think, means kind of half the amount of time or twice as successful in finding the docking zones. Rachel Brady and her team at the National Center for Supercomputing Applications did a volume visualization tool where they went and they have some fibrous material, we'll see a picture in a moment, and found that, and did some experiments and found that that was definitely a much faster way to do it in a virtual reality system versus on the desktop, even with the same software. Kenny Gruchala worked with oil and gas companies and found that placement of oil wells could be greatly enhanced using virtual reality. And Prabhat and a group from Brown University did the same for a flow visualization tool. So those are all, peer-reviewed, published examples of where virtual reality has kind of proven beneficial to science. But I don't want to discount necessarily these things here, which are anecdotes. So I mentioned in passing this, Gary Kinsland has a paper where he had just written a paper on his field of study, which is the, I don't remember how to pronounce it, but the crater in the Gulf of Mexico, created by an asteroid that probably killed off the dinosaurs, or at least one grouping of the dinosaurs. Anyway, he had just done a paper on that, and he was bringing that data into the cave where he's been working from time to time. But he was just going there to show a friend his data and how cool the cave was. And in the conversation, in a very short, like 10-minute conversation with his friend and colleague, he discovered a relationship that he hadn't noticed before, and he was able to go back and actually write a brand new paper just on that thing that he had discovered by spending 10 minutes or so in the cave. And so again, this is really where I kind of point to the amount of time in the cave is not necessarily the best measure of the value of the cave, because he got a paper just out of being in there for 10 minutes. All right. So now I want to talk about some concrete examples. And one of the things that the Advanced Visualization Group talks about when we talk about putting our data into virtual reality is that there's kind of these 3 levels of development effort. The one that requires kind of the least amount of work is the least complex, is if you have an existing application and it already has some sample data that you can bring right in. And so you can kind of learn how to use the tool. You can learn maybe drug docking. Maybe it's actually an educational application that has all pre-made scenarios that you can work yourself through. And so that's a good way to get started. But if you have your own data that you want to bring in, and there's already an existing tool, say you have your own molecular data and you want to bring it into a molecular visualization tool, then you don't really have to do a lot of work. You might have to figure out how to get your data into the format and find, how to find the directories and stuff like that to get it into that tool. Generally, not really super complicated, at least if the program's well written. But then kind of a big leap beyond that is where you actually need to develop the application itself. And then, of course, you could be talking months or years. Or if you're doing something simple, you just want to load in some vectors or something. For one, there might be an existing application if it's that simple. But 2, then you might be able to do it in a short amount of time. And a lot of this, if you're already familiar with tools like Unity or other kind of VR-ready systems, then you can, of course, reduce your effort at that. All right, so I want to look at kind of some examples of immersive visualization, and I've categorized them into 3 areas. One is where the tool was written specifically for visualization of a certain type of data set. The other is where it's kind of a general purpose scientific visualization tool or VR tool, and that we've maybe added an interface to add VR onto the visualization tool, right? And sometimes we just literally take a desktop tool and kind of stick a VR interface onto it. And then finally, this last version is where we have a visualization tool and we kind of steal its graphical output and transfer it over to a virtual reality space. And there are some successful ways of doing that. It's, of course, maybe not the best way to do it, but sometimes it might be the only way. So we'll look at a few of these applications. So I talked about the University of North Carolina. Here is that application, has a haptic arm in it for molecular bonding. And so this is the device, kind of the setup that they used as one of the conditions when they were doing their study. They later reduced it to kind of a desktop haptic display rather than this big one mounted to the ceiling. NASA Ames did some visualization of airflow around different aerodynamic shapes, such as the space shuttle here. And of course, back then, they used this old style boom interface. They had a whole group that was looking at human-centered interfaces. And this is the data set that Brown University, that I referred to, the Prabat paper, worked with to some degree. And so you can see, obviously, there's a lot of streamlined flow. There's pressures on the airfoils and things like that. I want to kind of cruise through these older ones. Here's the Crumbs one that I talked about with Rachel Brady here. So there are filaments. So in this case, there's, say, in this chicken embryo, there's a neural, you can see the dark blue neural filament. There's also some arterial filaments through there. So that's kind of a simple data set, but scientists would actually go and take that data and plot through it. Now, one of the interesting things then about this kind of goes back to what I said at the beginning, in that in order to be interactive, so we're talking 20 years ago, with the computers of 20 years ago, we couldn't see the whole data set. So in this upper right picture, the data set was all subsampled so that we're really not seeing it in full resolution. And one of the solutions to then see some of the data in full resolution was to just show like this small window of data. and then the white outlines show us the full size of the data set, and we're just going to focus on a little portion of that at any one moment in time. Here's one for atmospheric visualization. So this was taking a desktop visualization tool from the University of Wisconsin, and then Old Dominion University worked with them to add a virtual reality interface to that. And so looking at some atmospheric chemistry. So those were all kind of custom tools, or in one case, a custom Viz tool with an add-on virtual reality interface. Here's some general purpose visualization tools, which were popular again a while ago. So AVS, the Advanced Visualization System, had you had this plug and play. This is actually Explorer. So this is Iris Explorer, which is the same style system where you load in your data, you process it a little bit through these little blocks, these little modules, and then you output it to a renderer. And then at NCSA, we added a renderer that displayed the left and right stereo pair that was tracked. And so in this case, it was sent to a head-based display where you could see the stereo and walk around the data. Here's a VTK interface. So VTK is the visualization toolkit, which has a robust collection of visualization features. And then there have been multiple different efforts over the years to put that into VR. Starting, or early examples, Paul Reilich's VTK to Performer, but now Kitware themselves, and we'll revisit this, have their own interface to virtual reality. So that's makes things quite a bit easier. So those are kind of all older examples, but gave us a clue, a hint that virtual reality showed some promise. Here's some more sort of recent ones, and all of these recent ones are still running, but a lot of the examples of the pictures especially show them in the bigger VR systems. We'll get to the kind of head-mount display systems next. So here's a 3D visualizer. This is actually the Earth with all the locations of earthquakes in the past 100 or so years. It's kind of a general visualization tool. You can do other things. You can slice, you can isosurface, you can streamline. And you can see this is in a cave, and it was developed at UC Davis. Another tool from UC Davis is this LiDAR viewer, which really can visualize any collection of points. And so this is the one I showed earlier where it did the level of detail finding. So it loads in data specifically when you move around, and as you move away from regions, you'll see less and less of the points because you want to keep the rendering speed up. It also has things where we can select by painting, so you get the 6 degree of freedom movement. You can measure things with both hands by moving them around. And then you can do some things like data set comparison, which is the lower right picture, shows 2 data sets, one in red and one in green, and you can see how terrain has eroded or been built up over time. And of course, it then has a custom renderer with using the octree division in order to render literally, hundreds of billions of points at a time, because it doesn't display all 100 billion points. It displays the ones that are crucial for where you're at. Another tool using the same system was developed at the Desert Research Institute is what we call Toirt Samhlaigh, which is just Gaelic for volume visualization, which is what it does. It's a volume visualization tool. So here's a confocal microscope data set in the right, upper right, and then the other pictures are from ground penetrating radar, where these two researchers went to the Sahara Desert and literally had to go 1 meter at a time and measure this plot. And what they were looking for is the underground patterns of sand formation as the prevailing winds moved the sand around. And again, it has a custom renderer so that we can see the data fast, and that all uses GPU rendering. One from the University of California, San Diego is this one that uses the program called CalVR, and specifically here an archaeology app. CalVR actually takes plugins, so you can have a point cloud viewer, you can have a 360 stereo viewer. It's kind of a simplified version of CoVis, which we'll talk about in a moment, which comes from Germany. And so again, this one has both point clouds and artifacts, so you can measure where artifacts were found, but it's all custom written for archaeology. Here's one that's more an educational oriented tool, and this one is from Valparaiso. A re-implementation of a project from the University of Houston. At the University of Houston, they took their implementation and applied it to seniors in high school physics to see whether they understood or how well they would understand the physics that they'd learned from a book and see it in 3D. And what they found was, studying physics from a book, the students could answer the questions, they could get an A on the test, but not actually know the 3D nature of the fields. They could just answer the kind of the 2D questions. And so they found that with VR, they could, of course, the students were surprised. Oh, it looks like, it looks like this, it's billowing out in a certain direction, not just kind of splayed out in 2D. And so they found they have some papers, some peer-reviewed papers that demonstrate that. And so Valpo, Professor Will at Valpo, took that and re-implemented it for his CAVE, his flagship VR system. And they have a series of programs. The one that this picture shows is showing electric fields, Gauss's law. So it has kind of some basic things. It has point things and some vectors and some surfaces. So I have, we'll just play a few moments of video of Professor Will there doing that. So let's see. This may come up on there we go. I'm going to stand by the speaker.
So when I get close to that negative 5, you see that the electric field is radial integral. That's not perfect. But you can see the electric field over the
I'll skip ahead a moment here. So he moves this kind of point probe around, right? And so you can see how the field changes. We can't, he's not rendering everything at the same time, but lets the student explore. And he's actually teaching a class right now. That's what we're listening to, is him teaching students and demonstrating to them the 3D nature. You can see the double images because it's rendered in stereo. You can see as he walks around, or whatever student is wearing the stereo glasses walks around, the view also changes, but he's also able to change it with the hand controller. So we'll stop there. So that's a kind of a scientific educational tool. This is written in OpenGL and FreeVR, but his team is, he's kind of at the beginning of developing a Unity version to kind of modernize it a little bit. Oops, wrong focus. All right, CoVis, which I mentioned before, was developed at the High Performance Computer Center in Stuttgart. And it's more or less a general visualization tool that was a desktop tool, kind of like the AVS, where it connected modules together. And then it had kind of a well-integrated virtual reality rendering, and it can do all sorts of things. I've listed vector flow, isosurface, and point clouds, but it can do a lot more than that. And it has kind of a built right in virtual reality interface. Excuse me. Here's the application I talked about on the right. This is Professor Kinsland here looking at some of the data from the Gulf of Mexico. And then he also does work with oil and gas things. So here's some boreholes drilled into the surface. So we're actually below the surface of the Earth here, looking at data coming down. And so you can see different data from those boreholes. And so those are two kind of virtual reality examples for that. This one is a similar tool to what we've already seen. This is the surface of Mars we're looking at here, rendered with elevation, so you can see different 3D effects in it. One of the things, though, I want to kind of highlight here is the fact that it's, in addition to recording the data, this one also records the researcher, Don Sumner, talking about the data. And we're seeing it as we'll see it in a moment as a video. And you can see there's a little cone here that goes with her hand controller. And we've recorded, a video has been recorded of it from one perspective. But in fact, if you were in a virtual reality system, you could actually walk around her while she's talking about the data. So you can actually kind of now, she's only rendered from one side, but you can actually walk around. You can see exactly where the tip of her controller is pointing. And you're not actually necessarily limited to the one view that we are through the video. Let's see, can I start it here? Oh, there she is. Oh, wrong screen. There we go. So she's captured by a Kinect. So that's why she's kind of noisy there. But all that data is recorded, and then you can go back live and again, record it from one position or actually view it in virtual reality and walk around her as she points out the different ridges and different features of the data. And so they're recording these videos here. So they're looking for, like she said, where to place rovers on the surface of Mars. All right. And so that's kind of a neat feature where virtual reality has kind of double use. All right. So Paraview is an application that we've been working with here at IU for a long time. It's an outgrowth of the visualization toolkit that we talked about earlier. It's actually an advanced user interface on top of it. It was developed for the desktop, but in collaboration with Kitware, which is the company that builds, maintains Paraview, Idaho National Lab, and ourselves, we added some tracking to it using common tracking technologies, and then added it so that it would work in our cave, in the Idaho National Lab cave. Now recently, and we'll revisit Paraview in a minute, Kitware added their own interface for head-mounted displays using OpenVR, and I'll have a picture of that in a little bit. I mentioned at the outset that John Stone from University of Illinois at Urbana-Champaign will be coming next week, and so he's going to talk about VMD. But here's a picture of VMD running in our old cave up in Indianapolis. It has multiple molecular representations, so you can have ball and stick, you can have protein chains, ribbons, things like that. It'll also play moving data. So NAMD is a molecular simulation tool, which actually calculates how molecules interact with each other at the atomic level. And then you can play that information back and see how things work. So in this case, VMD was a desktop tool. It actually started as a VR tool, became a desktop tool with no VR, and then VR was added back on. So we'll talk more about that specifically next week. John Stone will be here to talk about that. A lot of people in the engineering field use MATLAB. MATLAB is a general purpose tool for visualization and mathematics. It does not have a real VR interface though, and so this is our example where we take the OpenGL, the graphics output that was going to go to the desktop. So in this lower right picture, you see a desktop view with some pictures behind the silhouette of the person. That same data is whatever took to draw those pictures is then moved into the virtual reality field view, and then the person can walk around them and it re-renders that. And so again, we call that OpenGL interceptor. It's kind of Shanghaiing the data. This particular application was developed at Duke by Dave Zielinski. And so it has a specific interface actually so that when you do button presses and stuff, you can send that back to MATLAB. And getting close to wrapping up our non-head-mounted display stuff, CVIS is a tool that's a joint project from James Madison University and Idaho National Lab. It's open sourced. It's mostly for looking at like terrain data and temporal data. So if you have, say in this case, a drone was flying over and scanning a point cloud scan of the data, you can actually go back and watch the drone move and control it and see what the data was at different places in time. And that's an open source project on GitHub. Here's a kind of simple project. So we're kind of going to gradually move into this notion of using Unity for our scientific visualization. And so this is an experimental render done by Kyle Summerfield at the University of Wyoming. And so he'd made it so that he'd use the Unity shaders to render these particles systems, and you can make different kind of particle movement waveforms and just kind of play around with it. So this isn't it's more of a sandbox toy experimental space than it is scientific visualization. But we're going to that's the way things are moving, right? So that was all the ones of that last little section I talked about. Those are things that still run. We can run those in caves. We can actually run a lot of those in head-mounted displays as well. The next kind of grouping that I want to talk about are ones that are really for consumer VR and that you can just more or less download now for the most part, and maybe in some cases you have to build it. But we'll look at Nanome, which is another molecular visualization tool. We'll take some of these tools that we already talked about and how they've been repurposed for head-mounted display, consumer level displays, and then we'll take a look at, we just kind of got a taste for how Unity is being used for accomplishing a lot of this at the consumer level. So some of those tools that we looked at already that run now in big displays use this system called Vrui, which is from UC Davis. And so this is LiDAR viewer, which we already talked about and saw in a cave. But now you can see it's got the kind of head-mounted display shape here. And so this was working in an HTC Vive, but it'll basically work on any OpenVR system. At the moment, the limitation here is that this is developed for Linux. And so it's consumers who are familiar with Linux in this case. So still kind of a restricted audience. It also can use the Kinect depth camera. That's like we saw with Professor Sumner. And basically, through this, I'm showing LiDAR Viewer here, but any of those tools that were based on Vrui, I mentioned a few. There was the earthquake one we looked at, LiDAR Viewer here, the volume visualization tool. So there are several visualization tools that are built on Vrui that you can run on OpenVR head-mounted display. I told you we'd revisit Paraview. So again, we collaborated with Kitware and Idaho National Lab to put Paraview into the cave, but some folks at Kitware then also went ahead and added OpenVR. Our cave effort predated OpenVR, I should say. OpenVR, they created an OpenVR VTK interface, and so for the most part, you can download Paraview, install it, and run it after initializing the VR plugin. And so you can load in your data into Paraview and click the VR button, put on your head-mounted display, and there you go. So pretty nice. Now you kind of have to be familiar with Paraview, which has a lot of options. Once you're in VR, your options are fairly limited. You can fly around. So Dave was trying this out the other day, Dave Reagan here. And so you can fly around. That works pretty well. You can do some slicing and clipping. The problem with that, though, is that wherever the wand controller is, that's where your slice is. You can't like put a slice and then leave it there. It has some kind of simple measuring tools. The menu interface is a little wonky. And really, we discussed in our discussion, kind of if you had somebody sitting at the console operating the visualization commands, acting as your voice recognition system, that's probably kind of how it would work best at the moment. Again, I want to revisit VMD. So we talked about VMD in the cave. VMD can also render for head-mounted displays. And in this case, it kind of renders, it does actual ray tracing. It does it for 360 rendering, which you can do live. And then once you've got the 360 sphere, you can kind of look around any direction you want in a head-mounted display. You can output that as a movie and then upload it to YouTube. And so here we are. This is watching on YouTube in a single view. So you can take your phone and kind of move it around like this. But you can also play YouTube in stereo on your head-mounted display. And so then you get that. And of course, John will talk more about that next week. Here's another here's a simpler example. This one is web distributed. And so it uses WebVR, which lets anybody kind of easily download it and use it, just to have the URL for it, which actually is right here at the bottom of the slide. Uses 3JS, correct? Yes, and WebVR. And some of the things are pre-rendered, so like the background scene here is pre-rendered. It's possible to render those all as individual stars, but then you have to load all that data onto your phone first. And so really, it's just for performance sake, we can pre-render that. And that was done as a collaboration with our Advanced Visualization group and the IU Astronomy team. All right, so those are some examples now that you can kind of get running right on Unity or right on consumer VR space. And so to close things up, I want to talk about kind of where we're at with developing and downloading and what Unity and Steam have done to kind of promote VR in general, of course, that's a given, but also a little bit they're promoting science, maybe unintentionally, but promoting the ability to do science, right? So Unity is a nice platform for developing things. It's meant for games, but you can kind of shoehorn in some other things, especially using the shaders. And then if you want to upload it and easily download applications, you can use the Steam store platform for that. And so Unity, like I said, is a game engine. We're repurposing it. I already said all that. It's Unity itself. While you can open source your Unity project, Unity itself is not open source. So A, it changes a lot, so you have to kind of keep up with it. And B, if the Unity company ever decides to go away and not give us their source code, then you're either stuck with a running version that you'll never be able to upgrade, or you're out of luck. And then Steam, as I mentioned, is kind of a distribution platform, and a lot of up-and-coming scientists will be familiar with it because they use it to download other computer graphical interaction tool experiences. So here's an example. This one's from Idaho National Lab. This is a volume visualization tool, kind of similar to the one that we saw with the Vrui application, Toirt Samhlaigh. This one, again, uses the OpenGL shaders to put kind of shoehorn rendering into Unity for computer science. and it uses the Unity user interface here. This is on the desktop, but we can take our Unity VR plugin and apply it there. It's in the process of being approved for open source through the lawyers at Idaho National Lab. So within a few months, a month or two, we hope to see that. And again, it uses GPU rendering. For those of you familiar with volume rendering, it uses Pascucci's multi-res indexing system so that it kind of has this binary pattern of things so that as you get closer to things, the resolution can be improved. And when you zoom out of things, you can kind of get the overall feel, but you don't have to see all the data. Harking back to what I said about keeping your data limited for 90 hertz rendering. Here's an application that you can just download from the Steam store. It's called CalcFlow. It's from a company called Nanome, which also, in the next slide, we'll see they have a product called Nanome. It's been open sourced, and so you can get it from GitHub. You do have to build it on Unity, but you can get a personal version of Unity for free, so you can run your own version of CalcFlow and modify it, but you don't have to. You can also just download the pre-compiled app from the Steam store as well. It comes with a tutorial, so you can learn how to use it. You can see that you can input mathematical formulas and see different patterns, and then sample it, like in this, in the lower right here, sample it on a grid to see different data values, or in the upper one, kind of show the surface, you know, of a plot. And again, you put formulas input into it, and so it's kind of an interesting way to do it. Whether the user interface is the best, it's kind of yet to be seen. We probably can do some work on that. And then that was developed by this same company that has done this Nanome molecular model visualization. I don't have it on the slide, but I'm pretty sure the guys who started this company came from the virtual reality club at the University of California, San Diego, where we saw some of the other apps from them. And so they have published this on the Steam store. It's free now. It used to be, I think, $60. They may still have a pro mode where you do have to pay extra if you want extra features. Again, it comes with a tutorial that shows you how to load molecules, twist them. You can collaborate. So this lower picture shows a couple people with avatars collaborating. You can do some of the things I mentioned with VMD. You can change the type of representation, ball and stick, or ribbons, things like that. You can build your own molecule in there, or you can download them from the protein data bank. And this one, like I said, just go to the Steam store, search for Nanome, and try it out. And then there's a lot of other applications that you can just go to this. All these are on the Steam store. But these are more on the education side of things. And so today we're talking about visualization, but I did want to kind of list these as possibilities if you want to see what can be done for viewing science data. But in this case, a lot of them have different tools. I'll talk more about this in a few weeks because this will be my hands-on experience. So, but there's kind of, I've categorized them as 4 different styles. Kind of museum style, so where you kind of go and you might go to like a science museum and do a little pre-done experiment, but do it on your own and have it and explain different parts of the body. Excuse me. It might be more of a narrative lecture where it kind of steps you through things. So here's a couple examples of that. It might be more sandbox where you can like play God in the universe and add planets and add asteroids and see how they work. This bottom one does that. So there's a couple of those. And then this lower right one is from a game called In-Cell VR, where you have missions to do, which kind of teaches you how the different organelles within a cell work together. And so we'll do hands-on for some of those in about a month. And so I put here Monday, March 25th, but I'm thinking I'm going to be out of town at the VR conference on that day. So I will have to find another day for that. It'll be here in this room for those who are here or want to come here, Franklin Hall, on the campus of Indiana University. And these are some of them that we'll probably look at. We'll probably look at Paraview and Nanome for sure, In-Cell, some of these kind of different from all the different categories I just listed. And then in April, our last one of these events will be April 10th, about a couple weeks before the semester wraps up. And we'll talk a little bit about Unity and using Unity, not just for science, but also for other tools. And so that is it. I don't have a clock anywhere. Oh, there's one. All right, that's pretty good. Did you have any questions?
Yeah, like how much actual work
Right. So I think a lot of it, because I mean, if you want to do just like a little science experiment, you can use Unity's physics. Oh, so the question was, how much is going on in Unity? But those are an approximation. Those are for games, right? So they're not really meant for science. And if you're doing something like at the molecular level, you know, the actions that happen on our kind of human scale are different. So yeah, so essentially, I think at this point you have to learn shader programming, and you basically have to just write your code in a shader, and then use Unity as some shell that you stick your shader in, and then Unity can do the user interface and the rendering for VR. But really, you're not really using Unity, right? You're
just using the tool.
Right. Yeah.
Okay. Because I can't really imagine putting a full data set in Unity and playing around with that. Like,
Right. I guess so he's asking about difficulty of loading in data into Unity. And so, yeah, I mean, if you had like a molecule, right, you could load in a molecule and that, you could just load that into Unity. You don't need a shader for that. And you probably could take, I mean, if you just had two molecules and you're trying to find the bonding between the two, you could probably write that without having to go to the shader level.
but you showed like the height visualization.
Right.
Stuff like that. Like,
Yeah, I think for that, you probably want to go to the shader.
is there another?
Well, people have used, if you're willing to go to Linux, you can use the Vrui one. And so for, you know, there's a group of people, if they're at a computing center that they do supercomputing, they'll have access to people who are familiar with Linux. And if you're in a computer science department, and so there are ways where you can just code that way. OpenVR itself, I mean, Unity uses OpenVR, which is Valve's system for connecting for head-mounted displays. You could write, you know, in C++ or C# or something directly to OpenVR. I don't know that I'm sure people are doing it, but I actually don't know any of those people.
Yeah.
But that's definitely a route you could go. And in that case, really, you know, if the rendering stuff would work regardless whether you compile it on Linux or Windows, it's just moving the compiler and then developing the interface based on the OpenVR stuff.
Yeah, CalVR has plenty of tools for like actually like moving around inside the person the ability to navigate it while you change it in the editor. That would be difficult, I would imagine.
Right. I was thinking of how I could rephrase that for the people who are listening, because we have several people listening.
Oh, I'm sorry.
No, that's okay. Yeah, right. Yes, so he was saying that yeah, Steam and Unity have all the tools kind of for moving around, right? But
the actual like creating the visualization and then allowing people to edit it while
right. So especially yes, the editing of visualizations would be right. You'd have to. I mean, it would kind of be writing from scratch. You're not taking advantage of.
you'd have to spend probably
Right. Yes. Right. Exactly. So the interface becomes most of the work, and because you're not taking advantage of what Unity or whatever gives you. I do know some people who've used Unreal for some scientific visualization, but I think for the most part, they're just loading in scientific data already formed, and then looking around and rendering it nicely. So Dave has asked if anyone on the remote side of things has questions. So if you want to type, I have the chat window up here. I can see what anybody's typing. Dave has a question.
So toward the beginning, you made a case for VR as a compelling or useful visualization tool.
Right.
Do you have examples of where the VR interface was more useful than just the interface on a normal monitor?
Right. So Dave's asking about a virtual reality kind of 6 degree of freedom interface versus a 2-degree display with a mouse, or maybe even a Space Mouse Magellan interface. So my best example for that is Crumbs, right? So let me see, I'll bring up that slide. Yes. Oh, did I repeat the question adequately, do you think? Okay. Let me find my Crumbs slide. There it is. All right. Yeah, so I think this lower picture kind of somewhat shows what's happening. So I mentioned before that there's this method of, in addition to visualizing it, you can actually plot the pathways, right? So this tools for path following bullet. And so one of the things, one researcher who was kind of guiding the development of the tool was doing was he would take a confocal capture of the sperm tail of a fruit fly. And so somehow this has to do with, you know, the ability of it to reproduce under certain conditions. And so the length of the sperm tail is what he was measuring. And it's basically like measuring the length of a ball of yarn by scanning a 3D copy of the ball of yarn and following that yarn through the data, right? And so that's where maybe in the near future, machine learning can do that for us, but 20 years ago, that was certainly not the case, and I don't even know if you can do it now. And so basically what you would do, so this, I don't have any pictures of that data set, unfortunately, but anyway, here, with this slice here, there's actually this, they're following along, say, the spinal cord of actually, I think, Alan's neck. He's looking at his own neck here, I think. But anyway, you can go through, Alan, you can correct me if I'm wrong. Alan's online, actually. So you could like plot down, move this view through the data and plot and follow the progression of the spinal cord. I mean, spinal cord's not as interesting example, this scanning a ball of yarn, right? But anyway, so you would then move that tool along, and as, you know, yarns are all crossing and stuff like that, as a human, you know, you're better able to say, well, you know, it's not doing a 90-degree turn or anything like that. It's following along, and everything's kind of fuzzy the way you've scanned it. And so the researcher who was doing that was at Chicago, and our cave was in Champaign. And so he would actually come down and spend like 3 hours in the cave doing one data set, save that out, and then, like I said, go back to his office in Chicago and do the analysis. So that's my best example. Oh, Alan says it's not his neck. Sorry. Right, yeah. So we talked about, so like Paraview is kind of the classic one. It's available on Windows and Linux and OS X. And it has a lot of features, loads in, you know, hundreds of different kinds of data sets. It's not really specific to molecules, so it'll load molecules, but it won't do like as good a job as something that was specific to molecular visualization. But for the most part, if you have like a 3D volume of data, it can load it. You can do slices. You can do we call isosurfaces, right, where the value doesn't change. And so where is it all, like if you have something that's being heated up, where is 400 degrees, you know, Kelvin or whatever, and it'll kind of show you that flow or the path, I guess, or surface, inner surface. And so, yeah, there's a lot of tools like that. I mean, Paraview is kind of the one is our go-to tool, but there are other tools that are along those lines. And then since we've been working with Paraview for so long, we put it in our big systems, you know, 10 years ago. And now they've kind of, as the consumer head-mounted display market has come online, they've put their own stuff in there where, as I mentioned, you just press a button, see it in VR. The inside VR user interface is, you know, has a lot to be desired. But if you're willing to go in and out of VR and do your manipulations and go in VR, or just have somebody sit there who's willing to, you know, do whatever you say, okay, you know, change the value to 400 or whatever, then that can work pretty well. And I imagine the user interface will improve as well. Question for Alan, what about Vol-Viz in Paraview to VR? So that is a good question, because Paraview volume visualization, do you know, Dave, does it use the GPU? It has some GPU features. They've been kind of, Paraview or Kitware has been adding GPU-based visualizations to Paraview over the last few years.
Yeah, I think they have.
Right. Right. So Dave's saying that there's like multiple methods, that there's a default that can choose between them. They also have optics rendering, I think. Is it NVIDIA's optics, or for doing ray trace style rendering?
Yeah, I think you're right.
Right. It's one of the issues with volume rendering, especially if you were, say, in a cave, is that a lot of times volume renderings, you know, we're pretending we're seeing inside the cloudiness of a volume, but we're actually rendering it from this way to that way. And we're kind of sampling data as we go through. And in CalVR systems, you have these corners. And so if you're rendering this way and then you're rendering that way, sometimes it kind of looks a little odd. I think for head-mounted displays, you don't have that problem because you're essentially looking in the same direction.
I have only very briefly tried on Paraview VR. Seemed to work.
All right, so Dave says he tried it and it seemed to work. Briefly, he's briefly tried it. With that, we'll come on over to, drive on over, and when we do our online stuff, we can, or our hands-on stuff, we'll have Paraview running for our hands-on demonstrations, which I'll have to reschedule. Here's a question from George. Any experience with a mirror or Viso? Okay, right. They used to have a mirror or a Viso in their cave. I do not have any recent experience with those, and even my old experience with those, which is over 10 years ago, was basically to get a sample version of it, a demo version for a month or so and play with it. So no, I don't. And I don't even know if they never got to an head-mounted display. Yeah, I don't even know what the current status of those products is as far as head-mounted displays. Sorry, George. All right. Oh, all right. He says thank you. All right. I'll wait another 30 seconds or so for any other questions. Otherwise, we'll wrap this one up. All right. Pretty good time. All right. Well, thank you for coming in person. And how many people do we have online? About 7 or 8?
Max of 12.
12. All right. All right. So that's good. Yeah, it's kind of ironic that we're doing virtual reality and most of our participants are distance. And so just a reminder, next week will be John Stone speaking. So I hope we'll have a lot of people for that because he's driving all the way over here. And he'll be talking that. And then after spring break, we'll have virtual tourism. And again, we'll have to reschedule our hands-on. And then some more folks from, including Alan, will be coming over from Illinois to talk about archaeology training in VR. And then we'll wrap up with Unity. So, all right. No other questions. I guess we'll call it quits there. And I'll stop the meeting somewhere here.